Hi everyone, I am Suniti Purohit. I am a research scientist at CSIRO based in Melbourne. So I'll be talking about an alternative iron agglomeration process that we call as lime magnetite pellet process or LMP process. So when we look at the current way of magnetite ore agglomeration, we start with magnetite ore, beneficiate it to concentrate, then the concentrate goes to a boiling stage, and the green pellets are then charged to a two-stage heating process. One is at preheating at 900 to 1100, followed by induration at 1200 to 1350 degrees centigrade. And then the impurated pellets are charged to the blast furnace or DRI processes for iron making. Now, what we are doing here is we deliberately oxidize magnetite to hematite and then charge it to the blast furnace and take out that added oxygen with additional fuel or additional carbon. So, the reason we do that is because magnetite has lower reducibility compared to hematite, and we need to oxidize it to hematite for it to charge it to the blast furnace or DRI processes. So with LMP process, we avoid that magnetite oxidation stage. So LMP again, it starts with the beneficiation of magnetite ore to concentrate, and then during the boiling stage, we add flux to form these fluxed green pellets. And then the fluxed green pellets goes to a one-stage induration process at 1000 to 1100 degrees centigrade in mildly reducing atmosphere. Mildly reducing because we don't want to oxidize magnetite to hematite, and it also ensures the formation of this CWF phase, CaFe3O5 phase, which we have found out to improve the strength and reducibility of the LMPs at higher CWF percentage. So these integrated LMPs with CWF phase are strong and reducible enough to be charged to these blast furnace or DRI processes. Now, we have been working on this process for a very long time now, 4 or 5 years. And so, first of all, I'd like to discuss some of the results from our previous work, and then some pilot testing results and cost and emission analysis. So this is a simple binary phase diagram of magnetite and lime. And what it shows here is that this CWF phase is a stoichiometric compound of 1 mole of magnetite, 1 mole of lime. It forms at about 28% of lime. And the diagram is also superimposed with these lime requirement of different iron making processes. So for the blast furnace, we have the lime in the range of about half stoichiometry LMP, which is 1 mole magnetite, half mole lime or limestone. And then so that's why we have selected this half stoichiometry composition for our pilot testing experiments. Now, obviously, for our laboratory experiments, we have looked into this whole range, starting from stoichiometry to half stoichiometry, to see the effect of composition on the percentage of CWF. And we have done experiments in this temperature range from 950 to 1050, and the minimum temperature is 950 because we want to ensure complete decomposition of limestone, and you don't want to go more than 1100 because we want to avoid the slag formation because that will affect the reducibility of the LMPs. Uh, the the reduction potential that we have chosen was based on the temperature and based on this log Q2 versus temperature diagrams. We have also done several experiments on studying the effect of reduction potential on the CWF percentage before, and these are some of the experimental results that I'd like to discuss today. So these are the samples that were indurated at 950 degrees centigrade. The samples were pure laboratory chemicals without any impurities in them, 99% pure. And the LMPs were found to produce CWF within about 5 minutes of reaction, and we saw about 55% of CWF within 30 minutes of reaction, and that is near to the equilibrium percentage predicted by the phase diagrams. These are some of the SEM micrographs of the samples produced using pure chemicals. And the LMPs were heated at 850, 950, and 1050 for 1 hour. And what we're seeing here is that the CWF phase has a platelet-shaped morphology, and they are interconnected to each other. And at higher temperature, we can see they are coming together and they're getting densified. The whole structure is densified. Now, all these experiments, these three experiments, were conducted at a fixed CO2 by CO ratio of 4:1. And obviously, at fixed CO2 by CO, when we go to a higher temperature, the reduction potential is higher. And therefore, we see some of the magnetite to oosterite reduction as well. But even with the presence of this denser FeO phase, we can see that the overall microstructure is quite porous with lots of open pores. Other than the CWF phase, we also saw some calciferrite phase like C2F, 2CaO.Fe2O3. They started to form at the beginning of the reaction, and then the percentage decreased with progress of the reaction. Uh, Other than this laboratory experiments, laboratory synthesis of the LMPs, we also conducted a scaled down version of the pilot tests on these on the small amount of these the LMPs from pure chemicals, and we found that the properties were similar to the industrial symptoms. So we decided to do the pilot synthesis as well as pilot testings. So the pilot synthesis were done with the magnetite concentrate from one steel and limestone ore, and both of them were the crossed to like 45 microns. The limestone were crossed. The concentrate were already at 45 micron. So they were mixed together, and 8.5% water was added. And then we made the seeds, followed by balling. And the balls were mostly it were plus 10 mm size, and then the green balls were dried at 110 overnight, followed by induration in a vertical shaft furnace, vertical tube furnace at 1050 for 2 hours. Now, we did the experiments using these crucibles, which had holes on the side. Uh, this is before we made the holes. So yeah, the height of the crucible is about 13 centimeters, and the hot zone of the furnace is about 10 centimeter. So we could fit in about 250 to 300 grams of the samples in every batch. And obviously there was a temperature distribution inside the crucible as well, plus minus 20 degrees. And we conducted the experiments at different CO2 by CO ratios. And because of this temperature gradient, we decided to take 3 layers of the samples, top, middle, and bottom, and analyze them under XRD and SCM. And these are some of the results. All the 3 layers looks quite similar in the XRD diffraction pattern. And we did the Ritfeld quantification of these 3 layers for all the experiments. And these are the experiments at different CO2 by CO ratios. At higher reduction potential, we see a higher amount of the CWF phase, about 21. But this sample, the top layer sample, also showed some FeO phase. By some I mean 30% of FeO, and we do not want that because FeO is denser; it will affect the reducibility. So we decided to stick with this 8.5:1 ratio for synthesizing this large amount of samples for pilot testings. And these samples had about 1.5 to 8% maximum FeO in them. And they have about this 15 to 16, 17 percentage of FeO, CWF in them. This is the SEM micrograph of a pilot batch sample. So prior to this one, we also have studied the effect of impurity oxides on the CWF formation. And we found out that the presence of silica, with the presence of silica, silica reacts with the lime to form this Larnite phase. Alumina goes into the C2F phase, 2CaO.Fe2O3, and it substitutes that Fe and form this Ca2AlFe2O5 phase. Magnesia directly goes to the Fe3O4. It doesn't affect the percentage of CWF much. And the morphology of CWF was not changed, and there was no impurity going inside the CWF phase. And the same results we found with the pilot batch as well. So the magnetite concentrate had about 4.98 percentage of silica in them and about 1.5 alumina. So we saw this C2F and Larnite phase as well. We can't see them in this SEM micrographs because these are just broken samples. These are not polished. So yeah, but you can see clearly this CWF phase, it still has this beautiful platelet shaped morphology in it. So the samples, India did it at 1052 hours, 8.5:1 ratio. We created a huge lot of them for this pilot testings. The all the pilot testings were based on the ISO standard test. The reducibility index were measured by the standard. Reduced 500 grams of samples at 900 degree, 3 hours. Um, 30% CO, 70% nitrogen, 15 liter per minute flow rate, and then we whatever the degree of reduction is after 3 hours, that's considered as the reducibility. Now the reducibility of LMPs were found to be more than 90 percentage. The acceptable reducibility of sinter is more than 60. For pellets is more than 70, and the reducibility of LMPs are quite high. Those are really excellent. And the tumble index, for the tumble index, the standard test involves tumbling 15 kg of samples at 25 RPM, 200 revolutions, and then the after tumbling, the products are sieved, plus 6.3 size fractions are called as the TI. And for LMPs, it was about 87 percentage. The acceptable TI for sinter is more than 65, pellet is more than 85. So the TI of LMPs is similar to the pellets and more than sinters. Now for RDI, again for RDI, we do the reduction in the same CO nitrogen ratio, same flow rate, but the temperature is 550, reduce it for half an hour, and after that the reduced pellets, they are tumbled at 30 revolutions for 30 RPM for 900 revolutions. And then the products are saved, and minus 2.8 size are called as RDI. And for the LNPs, the RDI was found to be 4.6 percentage, and the acceptable RDI for sinters is less than 20 percentage. Now for pellets, usually the papers report about 5 percentage plus minus. Yeah, so the LMPs have a similar RDI to pellets as well, and much better than the sinters. With the pilot testing results, we have also proposed a flow sheet of the LMP process. This is similar to the current pelletization process with blending like with a blender to mix the feedstocks together, followed by a boiling stage, then a conveyor belt to transport these pellets to to the kiln, and also dried when they are being transported. Then during the induration, we have considered two separate processes, one with rotary kiln, one with rotary hearth for the cost analysis. And then the pellets are cooled down in an annular cooler. The off gases, the sensibility of the pellets are being utilized to preheat the air that can be used in the heating stages. And then the cool pellets are screened, and the fines are then recycled back. Um, there will be a crushing stage involved somewhere in at this part. Now, we have analyzed the emission analysis for this LMP process by considering different types of fuel going into these kilns: coal, natural gas, recycled midrex, recycled blast furnace gas, and hydrogen gas, both blue and green hydrogen gas. And then we compared the LMP analysis from the LMP process, followed by blast furnace iron making with this base case iron making in blast furnace with 70% sinter and 30% pellet. And the results shows that when the LMPs are made with the natural gas and followed by blast furnace iron making, will reduce the CO2 emission from the base case by up to 18 percentage. With gray hydrogen gas, it's up to 13 percentage. And so gray hydrogen gas is where we are forming the hydrogen with the steam methane reforming, and there is no carbon capture and storage involved in that. So with that, we are producing 13%. These are the direct emission. And the green hydrogen gas, we can save up to 32% of the emission. Now, the capital cost of the LNP process we estimated for the flow sheet with rotary kiln and the flow sheet with the rotary hearth. With the rotary kiln, the capital cost is about $230 million. With rotary hearth, it's about 120 million Australian dollar. And then we also estimated the operating cost of the LMPs. So these horizontal lines here, those are the base case operating cost of the LMPs. So the LMPs produced using natural gas has operating cost at about 155, The green hydrogen gas is about 220, which is about $70 more compared to the natural gas. The blue hydrogen gas, which is with the carbon capture and storage, we will have about $20 more than the natural gas, the LNPs produced from the natural gas. Now, compared to new facility two, when we have the rotary hearth furnace, we will decrease the LNP cost by about $7 to $8, no matter what fuel we are using. Now, uh, we also have to check the sensitivity of the operating cost due to plus minus 30% change in all these cost parameters, like like this magnetite concentrate, fuel cost, and capex. And what we see here is that the operating cost is highly sensitive to the magnetite concentrate cost, followed by the green hydrogen cost, followed by blue hydrogen, and then the capital cost. So with this, I'd like to conclude my talk. So what we find so far is that LMPs, they are highly reducible. They have lower degradation reduction degradation index, and they have good thermal strength and suitable enough to be transported or shipped to different parts of the world. And they are complete saleable products. They're associated with low carbon footprints, and they're economically attractive options as well. And we so far we have seen mild weathering of these LMPs, but we again we need to do more experiments on this area. But the results from the pilot testings and the cost emission analysis suggest that the LMP are potential feedstock for the blast furnace iron making, and also in terms of the properties like strength reducibility, they are suitable for the DRI operations as well. However, the chemistry needs to be adjusted for the DRI process, obviously. So to wrap up the talk, I'd like to thank my team, the supervisor team, Mark Hansby, Keith Vining, Jeffrey Brooks, and Akbar Ramdhani for all their help in conducting all this research. And I'd also like to thank Matt Kilvan, and also Li Ming Lu for their help in balling and pilot testing, and also especially to Li Ming for having this discussion about the suitability of LMP for the iron making processes. And thank you everyone for listening to the talk. And I'll be happy to answer all your questions after this recording is over. Thank you.